Getting the access token to the client in a secure way is one thing. But that's not the end of the story. Since the client isn't allowed to read the access token, how does it know who the user is? That problem is solved with OpenID Connect, which is an extension to OAuth. I'm Roland Guit for Duende Software, makers of Identity Server. We help you to create secure applications in your organization. OpenID Connect allows for an additional token called the ID token, also known as the identity token, which the client is allowed to read. It contains information about the user's authentication event at the authorization server. OpenID Connect also introduces identity-related scopes, which are groups of user claims that can be included in the ID token, so the client has access to this information. For example, the profile scope. That is defined in the OpenID Connect standard. It consists of the first name, last name, and a couple of more identity-related claims. Apart from predefined scopes, custom scopes are also allowed. There are also request parameters that are added by OpenID Connect, like login hints, which let the authorization server know how to handle the login, and locale with region information. The identity token is also a JWT with a header, payload and signature. And where the access token has to be validated by the API, the identity token has to be verified by the client. You can see its structure looks similar to the access token. It contains information about the authentication event, the sub and the user claims that were added by requesting identity scopes. Here's a slide showing the complete flow with OpenID Connect. First, the code is obtained from the authorization server in the same way I explained earlier, and it is sent to the client. The backchannel will include a special scope called OpenID that will instruct the authorization server to return the identity token. The backchannel request will now not only return the access token, but also the identity token. The client should now validate the identity token in a similar manner the access token should be validated by an API. After that, it can start a local session. For a web application, that means reading the user claims from the identity token and putting them in a session cookie. Here's an example. An ASP.NET Core MVC application where all actions in the controllers require authorization. But what does that mean exactly? Well, that is determined by the code that configures the authentication handlers. In this case, one for a session cookie and one for OpenID Connect. Both will register a scheme with a name. In the OpenID Connect handler, the name OIDC is explicitly configured. In the cookie scheme, there's no explicit name. In that case, the default name cookies is used. Schemes have actions they can perform. Authenticate will construct the user's identity. Challenge will initiate the authentication process, and forbid is the action that happens when users try to access a resource they are not permitted to access. For the cookie handler, for example, authenticate means extracting the user information from the cookie, and challenge will redirect to a login page, /account/login by default, and forbid will redirect to a page indicating access was forbidden. In this configuration, we're telling ASP.NET Core to use the cookie scheme for all actions. Cookie authentication defaults.authentication scheme is just a static string with the name of the scheme. There is one exception to the rule. For the challenge action, the OIDC scheme should be used. That means that when a user's identity has to be constructed, it will be taken from the cookie, and the local redirect will occur when a forbidden resource is accessed. But when authentication is initiated, the flow configured in the OpenID Connect handler will start. That flow is selected here. Code means authorization code flow. The rest of the code configuring the handler is setting the authority and that's the URL of the identity provider it should trust, and the client ID and secret needed to redeem the code for the tokens. And of course the scopes to request. ASP.NET Core will request the OpenID and profile scope by default, but if you want to be specific about it, the scope collection can be cleared. As mentioned, OpenID is a scope defined in the OpenID Connect standard, which is needed to get the identity token. Profile is an OpenID Connect scope that contains user claims, but in addition to claims, the application also needs an access token to be able to call the API. So the API1 scope is requested here too. ASP.NET Core will automatically map the user claims in the identity token to the session cookie. Only the claims that are present in the mapping table, which is filled with common claims like name. All claims that have to be mapped which are not in the table should be explicitly configured, like website here, which is a claim that is returned as part of the profile scope. There's an endpoint called the user info endpoint on the authorization server, which can return the user claims too. If the handler is configured to use that, the actual identity token will only contain the subject ID, and an extra request will take place to get the other claims from the endpoint. The advantage is that when there are many claims, the identity token can become too large, and this setting prevents that. Setting save tokens to true will store all retrieved tokens in the session cookie. In that way, they can easily be retrieved when they are needed. In this part of the code, for example, where the API is called, the getTokenAsync extension method on HTTP context can be used to retrieve the stored tokens. Here the access token is fetched and used in the authorization header of the API request. The rest of the configuration disables the conversion to non-standard claim types when mapping occurs and hides the fact that we are using ASP.NET Core and the version of it. Finally, by specifying the name of the claim that contains the username and role, ASP.NET Core will know what claim value to retrieve when the corresponding properties are used on the claim's identity object. So now, by simply calling require authorization, or by using the authorize attribute, the configured schemes are used, and authorization policies can be used too, like I showed in the previous video. Now with all that in place, let's run this demo that can be downloaded here. 3 projects are started at the same time. The identity provider using Identity Server, the ASP.NET Core MVC client, and the API. The MVC application shows this landing page. For that, there's no authenticated user needed because the action is decorated with the allow anonymous attribute. Other actions, such as secure for example, don't have that attribute, so they do require a user to be logged in, because we've configured that requirement to be the default. Now when I trigger the secure action, the MVC application will see that the action requires a logged in user, and call the authenticate scheme action using the cookie handler, which will indicate there is no such user. So now the application calls the challenge scheme action, which is mapped to the OpenID Connect handler, initiating the authorization code flow. A redirect to the authorize endpoint occurs to the identity provider, passing in the needed parameters. And after validation, the identity provider shows the login screen. When I now enter my credentials, Bob with password Bob in this case, a browser redirect back to the client occurs, completing the front channel part. Now the server-side client, via a backchannel request, exchanges the code for the tokens. ID token is validated and read, and an encrypted session cookie is set in the browser that contains the claims and the tokens. And this demo application just echoes back what is in the cookie, so we can easily see what's happening. So now the user will be able to access the application as long as the cookie lives. And when the API is called, the MVC application will retrieve the access token from the cookie on the server and do the call to the API with the access token in the header. The API will validate the access token, and the response from the API just echoes back the claims in the access token in this case. Once the access token is obtained, we have to think about managing it. It expires after a short while, typically after an hour, to mitigate the risk of it being stolen and attackers having access to resources for a long period of time. Users are likely to use the application for more than the lifetime of the access token. So how to get a new one when an access token expires? Well, the flow could simply be restarted, but that would be a very bad user experience. The browser could suddenly redirect to the login page while a user is entering data, or using the application otherwise. That's why for interactive applications, often refresh tokens are used. This is yet a third type of token that allows the application to get a new access token in the background. It has to have a longer lifetime than the access token. 30 days is not uncommon. To get the refresh token, the offline access scope must be requested from the authorization server. And of course it has to be configured to allow that for the client. The response will look like this. There are 3 tokens now. And now when the access token expires, a new one can be obtained by sending the refresh token to the authorization server, which will return a new access token. But what have we gained here? The refresh token can be stolen too, right? That's true, but since an access token is self-contained, it can't be revoked. Refreshing a token requires the client to contact the authorization server, and at that moment the request to refresh can be denied. The organization owning the server may have detected an attack, or maybe an employee is leaving the company. It is also common practice to give users the opportunity to revoke their own refresh tokens using a page like this. Important to keep in mind is that when a revocation happens, the access token will still work until it expires. So its lifetime determines how quickly a user can be kicked out of the system. There is also a revocation endpoint that exists on the authorization server, which can be used to revoke the refresh token. It is meant to be used by clients, for example when users explicitly log out. What does it look like in code? Well, on the authorization server, identity server in this case, the offline access scope must be allowed for our client. Now the client can simply request it and the refresh token will be part of the response. The Microsoft OpenID Connect handler, however, doesn't have built-in support for token management. For that, an open source library, Duende.accesstokenmanagement.OpenID Connect, is available. It automates token caching, lifetime monitoring, refreshing the access token, and it has support for refresh token revocation as well. The necessary services must first be added to the DI container, and then a named HTTP client can be configured by using the extension method provided in the package. This HTTP client will now have the needed extra functionality. All that's left to do is get it from the factory and do a call with it. In the cookie handler, now the on-signing out event can be handled, revoking the refresh token with another included extension method. To revoke the token, all the client has to do now is call signout using the cookie scheme. And that was the introduction to OpenID Connect. I hope you enjoyed it.